Hi everyone, my name is Taylor Sparks, Editor-in-Chief at Integrating Materials and Manufacturing Innovation. I've got a new paper to talk about today. This one is all about understanding how we model the microstructural evolution of complex grain structures. It comes to us from Yo and Bair at Oklahoma State University in Tulsa. So what do I mean by complex grain structures? Well, take a look at this figure. It's a pretty good example. It's showing you the triple junction between three different grains. You've got grain 1, 2, and 3. Each one of these individual boundaries can be characterized as having its own degree of mismatch and its own grain boundary energy. And so understanding how this microstructure will evolve has been challenging. The authors point out in the introduction that this is a complex 5D anisotropy. You've got 3 degrees of freedom related to the misorientation and then 2 degrees of with respect to the interface between the pairs of grains. So this is complicated to model. The authors do point out that the Spherical-Gaussian method has emerged as this good approach to incorporate atom-level data into these mesoscale simulations through phase field modeling. So what does this paper build on? There's quite a bit of prior art here they have to consider. First off, this idea of coupling Spherical-Gaussian method with the 2 phase field models, that was presented by Mullins. That was done in this paper where they introduced the gamma and the epsilon models. There's also this paper by Olmsted which introduced this notion of grain boundary energy and actually provided libraries that we're going to use in this paper. One of the innovations in this paper, how they use those libraries, we essentially created a switch function. We're going to do a calculation that allows us to say something is either similar or dissimilar to a known grain boundary orientation with its associated energy. So it's going to switch it to 0 or 1, could potentially be values in between. It says when an exact match occurs, the switch value is set to 1, applying this minima energy. And if there's a significant misorientation deviation, then that switch value would fall to 0, applying the base or the maximum grain boundary energy. And it says obviously intermediate misorientations could be between 0 and 1, but that's not considered in the simulation. So what did they actually achieve? If you take a look at this figure, you see an example, right? Here they're showing at time 0 nanoseconds, and here at some time past that. What the output is showing you, on the left it's showing you the time evolution of the equilibrium. Grain boundaries are shown in blue. The grains are in red. When you zoom in on this triple junction, you can see that sort of rough edge there. That's actually the faceting on the diffused boundary. And then in C, you're actually seeing the comparison with the other approach by Politev, and it's pretty good agreement. So what are some takeaways from this approach? Well, first off, they show that if you add anisotropy through the interface, then the gamma model could be more limited than the epsilon model. The epsilon model is more stable. So the gamma model requires the difference of the maximum and the minima to be sort of regulated, which is going to be sort of limiting. Another thing they noticed is that the variations in the microstructure evolution that they observed were highly dependent on the anisotropy through the grain boundary energy, but the grain boundary mobility was sort of negligible. Obviously, they've shown that they can accurately reproduce molecular dynamics. And they do add this caveat that there are some limitations to this study. First off, it doesn't have a large set of comparisons with experimental observations or comprehensive MD simulations, and it doesn't dive deeply into local interactions at these triple junctions, but it does provide pretty reliable basis for future exploration, and I hope you'll learn more in the latest issue of IMMI.